we've established that the product of net torque and time interval is the change in the angular momentum, the change in the quantity I omega. Quantity I omega is called the angular momentum, so that the product of net torque and time interval is a change in angular momentum. In the product of net torque and time interval, completely analogous to the product of net force and time interval, which is the impulse of a force. The product of the net torque and the time interval is the angular impulse of a torque. So, angular impulse equals change in angular momentum. Now, if we have equal and opposite torques about any parallel axis for the same time interval, this implies equal and opposite changes in the angular momentum. Obviously, if the torques are equal and opposite, then the product tau net delta t is equal and opposite for the two different forces, giving us equal and opposite results for the change in angular momentum. This implies that in an isolated system, the change in angular momentum is zero, that is, that angular momentum is conserved. Now we have a situation where two rotating objects interact. The first having moment of inertia 0.03 kilogram meters squared, and changing from angular velocity from angular velocity 9 radians per second to -3 radians per second, so that the product of the moment of inertia and the change in angular velocity, we give it by this calculation, and we get -0.36 kilogram meters squared per second. Changing from 9 radians per second to -3 radians per second is, of course, a change of -12 radians per second, and 12 times 0.03 is 0.36, so we get the change at -0.36 kilogram meter squared times radians per second. One of these meters can be considered a meter of radius. Multiplying that by radian, we get a meter of arc, and we get this change in angular momentum. The second object has to have an equal and opposite change in angular momentum. So its change in angular momentum is plus 0.36 kilogram meters squared per second. Its moment of inertia is 0.05 kilogram meters squared. So the product of the moment of inertia and the change in angular velocity has to equal the change in angular momentum. Change in our angular velocity is thus 7.2 radians per second, and given the initial velocity of angular velocity of -7 radians per second, we calculate a final angular velocity of 0.2 radians per second, adding the change in velocity, the 7.2 radian per second change in velocity, to the initial -7 radian per second velocity.